Hi everyone, welcome to 590 seminar. So our first presenter today is Katherine Kim. Katherine earned her bachelor's degree in ECE from Olin College of Engineering in 2007 and her master's degree in ECE from the University of Illinois in 2011. Katherine is a PhD student at U of I, studying power electronics and control for PV systems under Professor Krein. She's also the student membership chair for the IEEE Power Electronics Society, and, as it is her duty, encourages everyone to become a member or renew their PLS membership if they have not done so already. And it's only $13 per year for students. Katherine.
Oh, am I on? I'm not on.
Yeah.
Test.
There we go.
Test, test. Okay. A little bit loud. There? Okay. The bottom is, okay, yep. Okay, great. Well, I will be talking to you today about some of the work I've been doing at the end of last spring and this summer. And I've been working with photovoltaics for most of my graduate career here. So one of the most recent things I've been looking at is hot spotting, which is a phenomenon that occurs within a series string of PVs. And they've known about it for quite a while, and I'm kind of become more interested in the problem again and looking at it and more of the details and what's actually happening within the cells. So despite the long title, we're looking at hot spotting within cells. Specifically, I'm looking at monocrystalline photovoltaic cells. So one of the things that happens, and this is a really cool group, I think they're in Denmark, and they do thermal imaging of like larger pictures. So they're looking at, you can see the array kind of a big array of panels, but within some of them, we get these little hot areas. And like, for example, on this one and up here, we have certain cells that reach a higher temperature. And this is actually a large source of degradation. There's a number of different degradation studies that have been done on looking at large systems, and hotspots have been one of the fastest reasons for, or the reasons for accelerated degradation. So because of this, I wanted to look more into exactly what's happening and why it's happening and what we can do to protect against it. So first of all, let's go back to the actual PV panel. So this is a pretty typical panel that you have. And when I look at this, I see 3 strings. And you probably may not see that right away, but the way that it works is each cell is about 1/2 volts, so 0.5 volts. And in order to reach the voltages that we need to connect to utility, we usually put them in series. So all of these are strung in 1 string. And so there's actually 3 strings here. It goes from the top usually back down, and usually there's a little junction box behind here. And so that's kind of why they string it up and around, and then so you have the 2 ends of the string and you connect them in the junction box. And then around each of those strings, you have a bypass diode, which if you're familiar with photovoltaics, that's what they'll put around it to attempt to protect against hot spotting. But some of the modeling research that I've done has shown that you can actually still get hot spots that form within, even if there is a bypass diode, which is, and has been shown in a number of studies. So this is still a problem. It's not completely conquered by the bypass diode, although it does help. So we're always dealing with strings of PVs, and really it comes down to this. This is the culprit. So say we have that panel with 3 strings in it. Usually each string has 12 to 36 cells. The longer they are, the worse the hot spotting is likely to be. And the most common length is about 24. And the one I just showed had 3 strings, but they can have 4 strings. That's more common in some of the larger panels today. And partial shading, which is also a thing that we talk about a lot in the PV world, is one of the main culprits that leads eventually to hot spotting. and also reduces the amount of power that you can get out of the cell, which is really the ultimate problem. And once you have a hotspot forming, it will damage the cells. So let's just take a pretty simple example. You have the sun is shining down horizontally, apparently, onto this panel that you have against it. And say you have, a flock of birds like flying by, and they're just, they're migrating. I didn't have geese, so I used a duck. And he flies down, and he's just sitting right in front of your panel. And little does he know, he's causing a shadow on your panel, which, he doesn't know. He's just chilling. So what happens here, though, is this one shaded PV is not getting as much light as the other ones, right? So it's actually it's like a weak cell. It can't produce as much. And we'll look at the IV curves in a second, but it starts to act like a load, and it actually heats up. So it doesn't actually turn red, but it heats up. And if this heats up for long enough and at a high enough level, you can start to form a hot spot and actually begin to degrade the cell. Oh. What? What about him?
That's one of the insurance companies.
Yeah, it's he's causing the problem, so this is the thing. He's creating the shadow. Okay. You can use any animal you want here. So if we look at the IV characteristics of this will maybe help the electrical parts of us understand it better. So you have an IV curve, and usually we're used to looking at just the upper right hand part of this. So you have open circuit voltage, short circuit current, maximum power point. That's all we care about. But there's so much more. There's this whole other side. This is a breakdown region. And what happens is when our duct comes in, before the duct comes in, everything's working perfectly. So this is a string, pretend it's 24 going out further. And there's a string level converter, like inverter, controlling it at its maximum power point over the string's maximum power point. So luckily, these are all ideal, everything's the same. So we're at the maximum power point of every single cell. But when our duct lands in front of our cell, we have a change in the system, right? The string converter is still going to try to maximize the entire string power. So it'll actually find a current it's not going to be this maximum power point anymore because the system's changed, but it's still going to be probably higher than the short circuit current of this shaded cell. So it'll kind of equalize to some value. And if it's above this short circuit current here, instead of having a positive voltage on this cell, we're going to have a negative voltage, and it's going to become a load. So it's going to sink power rather than provide power. But to the overall string, this is still the optimal point to act. So that's why we get this reverse bias happening here. And this can form into a hot spot. Okay, so the next question is, so we know this happens, but how much does it need to be in reverse bias in order to start causing damage? So the question I'm looking at this is what level of reverse bias actually causes permanent damage, and how can we just better understand what's happening within the cell when it becomes hot spotted? All right, so to investigate this problem, I looked at getting some cells off of eBay, because that's the best place to get them. So they come as individual cells, and these are the ones that you would put on a real installation. So if you did a do-it-yourself kit, and they have a whole bunch on eBay if you I guess are interested, then you can go get these kind of cells and then solder your own connectors on. But these are pretty common. So the next question is, so I'm only looking at this one type of cell, but I want to try to not just study this one cell, but how can I make it more general? So if we're looking at reverse biasing it, we actually want to look at power. So the power is generally that it can create is proportional to kind of how large it is, because that's its area where it can convert the light into current. So if we're going to reverse bias it, we want to think about it in terms of power. In forward bias, this cell can take, it's a range because it's not exactly the same, but I just assume like 3.5. So in 3.5 in the forward direction, produce power, I assume it can probably take that much in the reverse direction. And then we want to look at, once you go past that, how much more can it take? So we'll be looking at 1 times the maximum power point in maximum power in reverse, 2 times, 3 times, and 4 times. So based on these cells, we set up we did 12 different cells, and we're looking at them actually under dark conditions because it's easier to test, and also they would be shaded if they're reverse bias, but we're not sure exactly how much they'd be shaded, so just to make them all the same, we're just doing them under dark conditions, so no light. Reverse biasing at those 4 different levels of power, and I'm sustaining it for 1 hour in the reverse bias direction and conducting the tests for 7 days, approximately in a row. So it's almost as if you have a stationary object that's kind of blocking the PV panel. And this happens like during the day when the sun's coming over, you'll get a stationary object that will kind of shade the same part of the panel every day. So this is kind of trying to recreate that, but only for 7 days. And then we're looking at the IV curve during the test and after and before. Okay, so now we're talking about IV curves again. So I just want to take you back to this picture again. So this is the normal one with the sun, and this is what we are used to. If we look at a data sheet, it'll give us everything on this upper quadrant. But what we're looking at is no sun. So what that does, all it does is it brings down this to the origin. It intersects with the origin, and that means that there's no photocurrent. So really, you're just getting the effect of the diode. Okay, so and what I'm going to be looking at in this study is actually the reverse part of the quadrant, and future work is actually going to be looking at the forward part of the quadrant. We didn't see as much change in that area, so I'm focusing on the reverse part because that's where we're seeing some changes, and I'll get into that as we look at the results. So just to give you an idea, if we want to do 1 times the maximum power point, what it's rated for, we find the point, you kind of go backwards until you find the point that is equal to the power. So 3.5 watts being used as a load. And then the next set of cells is used at 2 times. The next set is 3 and 4 times. Okay, so if we look at, and I know this is busy, but we're going to go through it slowly. So this is kind of all 12 of them. And this is during the test. So what's happening as we're heating it up? And I'm going to take your attention just to these 5 here. And you can kind of see that there's not really that much of a change that's happening. Oh, sorry, also, so here, these 3 are reversed by 3.5 watts, so 1 times the maximum power point. These are 2 times, 3 times, and 4 times. So this is kind of like the most extreme case. So this is a lot of power is being thrown through these guys. So on the 1 and 2, we see that these ones, they're actually not changing that much during the test. Most of the effects that are happening here are related to thermal effects. So we're not getting too much of a change. I'm going to bring your attention to the ones in orange. So actually that one, we kind of had some weird measurements. We see some changes, we're not sure. These 2 are, we see some changes. So sorry, the blue one is the original one, and then the red and the black are after 20 minutes and after 30 minutes, so at the end of the test. Sorry, I should have explained that earlier. Oh, ABC is just 1, 2, 3. I took 3 samples of each one, so there's no, these are just, they should be equal. They just happen to be how I numbered them. So I think these are just the set. So A, B, and C have nothing to do with it. Yeah, there are 3 different cells. Yes. Is that clear? I just want to make sure everyone's on the same page. Okay. So we do see some changes during the test here, and we're putting some more heat into these, so it makes sense that they're going to be changing a little bit more. And the most interesting ones are these ones in red. So these 4 here, so this is 3 times and 4 times the maximum power point, and we're seeing some kind of crazy changes that are going on. So the blue is before the test, and then red and black are as they are being tested. And I'm going to draw your attention to these 2. So 4 times the maximum power point, A and C. And so I've redrawn them here so they're easier to see. So what's happening between these 2 is something called second breakdown. And in this one, we're actually putting 4 times the maximum power point through this one. And we're seeing a little bit of changes through the heating, but it's pretty good. It's not breaking down. It's doing fine. It's doing what we would want it to do. It's taking all the power and not damaging the cell. This one, we're seeing this weird thing. And this is, I remember when I first saw this, I was really confused because I would see this with a few of them, and it's weird. So we're actually ramping up the current. So we're forcing the current up slowly in order to take these measurements. But what's happening, and the IV curve does not actually go hook around like this, but what's happening is as we measure up to here, we're heating up the cell. It's changing its IV curve, and it's becoming like this. So it's kind of moving up and to the right. We take the next measurement, it heats up more. The IV curve moves up this way, and the IV curve is moving up as we're taking the measurements. So it's very thermally sensitive to what we're doing. We're just putting a little bit more power through it. And this is happening in a couple milliseconds, this whole sweep. I think, I forget how many, but less than a second for sure. So this is a very fast reacting system. And so what's actually happening, so if you're not an IV curve person, what's actually happening here is that all of the, so this is a thermal image, and the second breakdown one, all of the power is just going through this little corner. So this is the hot spot within the cell. And you can see that this one over here, the one that's not breaking down, is kind of, it's like a nice glowing color. It's kind of even throughout. It's taking most of the current evenly throughout it. There's a little bit on the edges, but it's not so bad. But this one, it just has a huge breakdown point right there. And the temperature actually goes off the scale. These are the same scales, just so you can directly compare them. But you see all of it is going into that corner. And so what's happening as we measure this is that that's like pushing through that weak point in the corner and going totally through there. And we're losing the nice characteristics of the PV cell itself. So now we want to look at, so that's what's happening while we're testing it. Oh, simming, yes.
So go back to slide 12.
Yes.
So with this, so I don't, you're not showing what's happening in the generating power part.
Mm-hmm.
But I mean, if based on what you said before, if nothing is changing, wouldn't it be better now? Because now, if it's hot spotting later, wouldn't it be drawing less power because now the IV curve is shifted? So if you're drawing the same current, there's less voltage.
It's a good observation. It actually does, this one, okay, 2 points. I'm not showing where it's going here, but actually the heat does change the IV curves in the forward one. I could have shown it for the test here. It will just kind of shift the everything inward towards the y-axis. But that's just a thermal thing. And then, yeah, so it is actually going to draw less power, but it's all going through such a small point instead of being spread out that there's likely damage happening in that corner. So it's still more than it should be going through that small corner. So it's still damaging the cell, even though we're not, it's only that one cell, but then it's a weak point in the cell. That follow, kind of. Okay, we'll get to the next part, and then you can come back at the end. Okay, any other questions at this point? Am I okay on time? Okay, I'll keep going. You can ask questions then. So then we wanted to look at, so we see that this hotspot's forming, right, the second breakdown, but does that matter? Is it going to actually affect it? And that's the real question I wanted to see. So if we kind of go back to these, we actually had some bad things happen. This one had some inconsistent measurements. It just never, something was weird with the cell and the measurements, so we ended up just taking that one out. This one actually broke on day 5, and I was very sad because I couldn't finish the test. So those two kind of have to just ignore for this study. But then if we look at these again, these are the same ones, and this is over the 5-day. Actually, it's over from day 2 to 7 because our day 1 measurements were not so good. But that's why we repeat tests many times. So we're actually not seeing that much of a change throughout this from day 2 to day 7. So it looks like there's nothing physically changing within the cell. These two, I don't remember. These ones did not go into second breakdown. So even though we reverse biased them, they did not get a pinpoint weakness and where all the heat went through. So these we actually don't see too much of a change. This one a little bit because we're putting 4 times as much the maximum power point rated current through it, or power through it. We do see a little bit of a change. So that's interesting to note. These, although these were the ones that did go into second breakdown, this one, the A3, has a small amount of change, but these ones have a really clear change in the reverse bias characteristics. And I'm only including 3 days, but the trends did follow that. So we're seeing a really clear change in the reverse characteristics of the ones that went into second breakdown. So this leads me to believe that second breakdown, if it goes into that stage, you're actually doing damage to the cell itself. And that's really the threshold that we want to avoid going into. So from this initial study, after examining the 12 monocrystalline silicon PV cells at the 1, 2, 3, and 4 times the reverse maximum power point, when second breakdown does not happen, we see minor changes in the test or during the reverse bias test, and we don't see any really clear permanent changes in the IV characteristics. When it does go into reverse breakdown, second breakdown, we see much larger changes, that weird kind of hook thing that we see, and permanent changes are more likely to occur, although not absolute. So based on this, since we're kind of increasing here, looks like a safe region. So my initial conclusions would be that 2 times the maximum power point in reverse looks like a safe level that we can let the PVs go to without breaking down and damaging the cell further. Of course, we want to keep working on this, and I'm going to be working on this semester. We look at probably some polycrystalline and hopefully some thin film. We really do want to measure them under illumination, because the things that I'm missing here is I'm not getting a sense for that photocurrent. So we want to see if those hot spots are affecting how it's taking the light and converting it into electricity. So that's another thing that we're going to try to do, and use that on a halogen light setup that we have in the lab. And also to conduct it for a longer time. This was only 7 days. We really want to see if it can go for maybe a month or something that would be a little bit more long-term, because really we want to see how it's going to act over 25 years, because that's the lifetime. So acknowledge all the people that go into funding and helping, and thanks to Chris Barth for his help with some of the microcontroller, and Kevin, of course, for getting everything together, and the rest of you guys for just being wonderful. And I'm open for questions. Oh, yes. Any questions at all? Oh.
Thank you. So you found that 2x was sort of a safe place. How does that correspond to the duck? As in, if you have 12 of these, say in a string, and they can all produce full maximum power, right? So see if they can be a worst case, it can be an 11x power through one of these cells. Have you done any correlation between the shading pattern and how much shading does that constitute?
No, that's actually an excellent next step, is looking at what does that mean for the length, and it matters how much light you have, right? If it's at 1,000 watts per meter squared, or if it's only 50, and then if one gets shaded, that would be the worst case. If multiple, it's not as bad. I haven't looked into that. That's probably some of the next steps. I have to review what I have done a little bit of modeling work with that, but.
So a single cell-sized duck would be the worst case.
Yes, actually, I think it's actually a portion of the.
Fair enough. Yeah.
Yeah, that would be the small ducks are the worst, definitely. Any other questions at all, Terry?
So I was wondering if you did the.
Is it on?
Is it on? I don't know. Anyway, I was wondering if you did the thermal imaging thing at each time. Does the hotspot move? Is it always in the same spot? Once, is that just a defective part of the or something? Or?
I did not do it every single time, but I did it on a few, and it always comes up in the same spot. So I kind of yes, yeah, and there's various literature points to different types of impurities. So if you have a particle of a different material, it actually will make a weaker point. But it's you can't really see them. You don't really know where they are. And they all tend to happen on the edges. So I'm not sure if it's a manufacturing thing. Probably they're more. They're all from the same eBay batch. So as much as that answers, I mean, I would think that. It could be, but I mean they're pretty well in there. And the literature I've seen all says that they tend to form in the corners and on the edges. So I think even in the, if you go way back, oh, I should have done this, not put so many animations. If you go back to this, you can actually see kind of like on the edges that these are forming. Maybe, like it tends to be that way on the edges.
That's usually when the silicon defects happen when you saw that cell, when you cut off the edges. Right?
Yeah.
If you have any defects, usually
right. Makes sense. Yeah, and when the one cell that broke, it broke right on the corners too. So if there's just more likely to have impurities there, that's like a weak point where it can go through the junction. Always a thing. Slide 11. All right, we're gonna do this.
Yeah. So from this picture, how can you say? Okay. I'll ask it anyway. But I was gonna say, how can you tell from this picture which one goes in the second breakdown? Is this the one that hooks around and it starts to shift up?
Yeah, and this is originally I didn't really, when I started this, I just noticed that this was happening, and then I looked further into what it really was. And so when it goes around, like have this curve thing, and this one was on the verge of breaking, so I think that's why it looks so weird. But yeah, when it curves around like that, that's an indication that the heat that we're putting through it as we measure it is affecting it so much. And I think it's that junction breaking down. Instead of going through the whole cell, it goes to that one corner, and so that's what we're seeing here.
Did you make up this term, second breakdown?
No, that's actually.
That's at the thing on the edge.
Its second breakdown is where instead of going through the whole area, it's actually for transistors. A lot of old literature has that terminology, and instead of going through the whole thing that it should be, it just goes through that one little point, and it's a failure within a transistor, and it will heat it up quite a bit. So essentially the same thing, only our diode, maybe it's in diodes and transistors, but PV is essentially a giant diode, so it just goes to one little corner instead of a small die. Any other questions? Roy? That's back there.
Can you avoid hot spotting with something like differential power processing or like a cascaded DC to DC converter?
Right. So with differential power processing, we're still working in strings. So if we went differential power processing all the way to the cell level, and actually if you did any set of control at the cell level, yeah, no problem. But it's when we put them in strings that you have the potential for this. The shorter the string, the less potential there is. But actually, as Professor Palawa kind of mentioned, it's hard to quantify which conditions are we actually going to have the reverse biasing happening. So in certain conditions, even in a 24 cells, which is relatively short in the standard, you can still get one reverse biased pretty past this level, past 2 times the maximum power point.
So if you just increase granularity then.
If you just the short answer would be decrease them, make them maybe 3 or 4, and then you'd be pretty good. Okay. If you really want to be safe, you'd do every single one, but studies have shown that's actually not. It ends up being more work than it's worth.
Yeah.
But good question. Are we on time? Okay. Okay. Okay, we're perfect. I guess I'll end it there, and thank you very much for listening.
Actually, a quick announcement while Shibin's setting up. Chris Barth is going to hold a meeting for EOH right after this at 5 o'clock. So if you're interested in participating in a project, stay after the seminar. All right, so our second presenter is Shibin Qing. He received his Bachelor of Engineering degree from Huazhong University of Science and Technology. He's currently pursuing a master's degree at the University of Illinois. And his current research interest is power electronics in PV applications. Shibin, take it away.
Oh, thank you. Good afternoon, everyone. My name is Shibin, and today I'm going to present our paper titled A Distributed Approach. Can you put it in full screen?
Everyone different.
Okay. Titled a distributed approach to maximum power point tracking for PV submodule differential power processing. So this is the outline of my presentation. And I will begin with a brief introduction to some of the background. So to begin with, as Katherine just introduced, PV modules are often connected in series to stack for a high enough voltage for the efficient operation of the converter. And the series PV configuration then create a well-known characteristic mismatch problem, where it's typically a result of partial shading or manufacturer variation or non-uniform aging characteristics. Because PV modules are connected in series, so they share the same string current. But due to this characteristic mismatch, their optimal operating current are often different. So which means all PV modules cannot work at their maximum power point at the same time. And then this problem motivates the development of distributed maximum power point tracking solutions. And nowadays, the two most dominant solutions are DC optimizers and microinverters. And microinverters is not very comparable to the topic of differential power processing today, so I'm not going to use that as an example. So instead, I'm going to use a DC optimizer system as an example, which is shown here. So in DC optimizer system, each PV is connected to a DC to DC converter, then to the central converter in a string. And the problem of DC optimizer system is that the whole power generated by each PV module has to be fully processed by this DC to DC stage before it comes to the central inverter. So even if you have a highly efficient DC to DC converter, because you are processing more power, then the overall power losses can still be significant. And the question is there any way we can overcome this limitation and do better? And the answer is differential power processing, which is shown here. So in this configuration, DC to DC converter are actually connected in parallel with the PV string, and they are typically configured as a bidirectional buck boost converter. So the bulk power generated by this all PV modules can go to the central inverter directly without any intermediate conversion. And the differential power processing converter only processes the power difference, which is typically a small portion of the whole power. And in this way, because we are processing less power, so the overall power losses can be reduced. So in this example, the power losses of the entire system is like cut by half. But the problem with DPP system is that each DPP converter need to operate two adjacent PV modules at the same time, and the input-output of these neighboring DPP converters are actually coupled to each other. So we have to look at the maximum power point tracking control in DPP system from a different perspective. Here is the DPP system, and the control goal of maximum power point tracking is to maximize the power out of this PV string, which is the product of string voltage and string current. And to do that, what we propose is to separate the control of string current and string voltage into two different control loops. So in the slow control loop, we program this central inverter to act like a controllable current sink, and it will perform the traditional perturb and observe method with string current as a reference, and it will try to seek the optimal string current. At the same time, because DPP converters, they are typically switching at a much higher frequency than the central inverter. So compared to the slow control loop, their time constant are like much smaller. So at any given time, for these DPP converters, the string current can be viewed as the fixed value for these DPP converters, which means in this control objective, current is fixed. And then the task of maximizing string power can be simplified to maximizing string voltage. And this is exactly what DPP converters are doing in this case. So here is the timeline of this control. So you can see discrete steps of string current update. And in between, there are DPP converters trying to maximize the string voltage. But then the challenge is each DPP converter only measures part of the string voltage. It does not have information of the entire string voltage. So how can we actually control the duty ratio of each DPP converter to maximize the string voltage? So there are several previous solutions. And the first one is equalizing the voltage of all PV modules, which is also known as virtual parallel operation. This is actually running the converters in open loop without any control. So despite the fact that it does not really require any communication or any local current measurement, it's actually not performing true maximum power point tracking, but only a approximation. So it's not the ideal solution. And then it comes the centralized perturb and observe method, which means the DPP converters actually take turns to perturb its duty ratio and observe the change in the string voltage. And this is done through a centralized communication and a central controller. In this case, again, we don't have any local current measurement, but it requires global communication, which is prone to single point failure. So it's also not ideal. But recently, there's a new solution proposed by the Dartmouth group, which is called multi-level power point tractor. And actually, it can achieve true maximum power point tracking without like very complicated form of communication. But it still requires synchronization, and it requires local current measurement. So still, it's not ideal. So what we are going to propose is a solution that combines the advantage of all of these solutions, and it requires no local current measurement. It requires only neighbor-to-neighbor communication, but it still performs true maximum power point tracking. So again, this is our control design objective in summary. And actually, we have done that with hardware experiment. But before that, let's just go through the mathematics behind this control algorithm. So I'm going to explain the control algorithm with the simplest 3 submodule 2 DPP system. So here is how this system looks like. So in this case, we have 3 submodules and 2 DPP converters. And let's define the state vector of this entire system to be xk. And we actually partition this xk into 2 different parts. And each converter only keep track of their own part of xk, which is actually x1k here and x2k here. And this x1k actually consists of D1, which is the actual duty ratio of converter 1, and D2 hat, which is an estimation of duty of D2. That means D2 hat is actually what converter 1 think converter 2, the duty ratio of converter 2 is. And similarly, on converter 2, we actually store D1 hat and D2. And then we have zk, which is an auxiliary state variable. It does not really have a physical projection in the system, but again, it's partitioned and stored separately in 2 DPP converters. And these 2 DPP converters, they can exchange information through neighbor-to-neighbor communication. So they have access to the information stored by the other converter. So that's the state vector. And then recall the control objective is to maximize the string voltage, which is equivalent to set the gradients of the string voltage to 0. To do that, we actually define 2 phi functions, which is phi1 and phi2, consists of v1, v2, and v3. And then we define the input vector to the system to be partial derivative of this phi function. And as you can notice here, the phi function actually adds up. If you add these terms together, it adds up to the string voltage V0. And also, so this actually comply with the control objective to maximize the string voltage. And you can notice here, phi 1 is only directly measurable by converter 1, which is here, and phi 2 is only directly measurable by converter 2, which correspond to this separation here. So each DPP converter can separately measure its own input. And the only remaining question here is that how do we actually measure the partial? Because what we can measure is actually voltage. And to do that, here's the timeline of the system operation. So after each term, each round of information exchange, converter 1 will perturb its duty ratio by a small amount of delta D1, and all converters will observe the resulting change in their phi function, and they can approximate the partial as the ratio of change. And similarly, after converter 1 perturb, converter 2 can perturb its duty ratio, and all converters actually observe the resulting change here. So in this way, we can have all these input to the system. So to summarize how the system works, so it starts with the exchange of information between these two. So these two converters can share the information of state vectors and auxiliary state vectors. And then D1 and D2 perturb so they can measure the input. And once upon the receipt of all this information, they can update their state vector according to this function. I'm not going to go into details about this update function, but you are encouraged to refer to the actual paper for details of this algorithm. And then after this update function, it will just start another round of exchange of information, and the algorithm actually goes on and on. So to have an intuitive understanding of this algorithm, so let's take a look at the simulation of 3-submodule 2-DPP system case, which is shown here. These 4 parts are actually the 3D visualization of the string voltage as a function of D1 and D2. So X and Y axis are actually duty ratio, D1 and D2. And showing color here is the string voltage value. So in these titles here actually indicate the insulation condition on 3 separate PV modules. And so in this case, between time 0 and 2 seconds, we have 100% insulation. And from the second to the 4th second, we have 180 and 80% normalized insulation. So this is like insulation step change happened at the 2nd second, and the 4th second, and the 6th second. And here, shown here, is the actual trajectory of the duty ratio as the algorithm evolves. So as you can see here, as we start here, it quickly converges to the optimal value. And upon the insulation change here, here, and here, it will have a little bit overshoot and again quickly converge to a new optimal value, which, for example, in this area, correspond to this trajectory. So as you can see here, as the insulation change here, it starts at this point and slowly move to the optimal point. So here is another simulation of a 6-submodule 5-DPP system. So in this case, I'm going to simply if you have a similar setting of the previous simulation where we start at a certain condition and we have insulation change at these points, so they can all converge to the new optimal value. And what I'm trying to show here is that there are actually more flexibility in the design and improvement of this algorithm, that by having duplicate, like redundant communication, we can actually improve the property of this algorithm. So shown on the second graph here is that when you not only have neighbor-to-neighbor communication, but also when you can talk to the second neighbor, and then actually the converge can be speeded up. And when you can actually communicate to all converters in the system, and actually you can speed up the convergence even further. And why is this important? Because if you have a redundance in your system and you have a communication failure, then this algorithm can actually detect that and reconfigure itself to account for the communication failure. So as you can see here, at the second here, the communication between 1 and 3 actually failed, but it can recognize that and reconfigure itself so it converges to a new optimal value. So yeah, that's simulation. So how do we actually implement this algorithm in a real DPP system? That's what I'm going to introduce next, is hardware design and laboratory testbed. So let's begin with a look inside the PV junction box. So as Katherine just introduced, so actually in each PV module, it typically consists of 3 submodules, and you can access these 3 submodules through a junction box. And because we are trying to perform submodule level maximum property tracking, so in each junction box, we need to integrate 3 DPP converters. 2 of them actually balance the mismatch within a PV module, and another one actually need to reach across to the next, to the first submodule in the next PV module. And nowadays, there's a growing trend to shrink the size of converters to actually fit in the junction box of a PV module. That's because a separate enclosure for power electronic circuits actually can significantly increase the cost of the overall system. So to do that, we noticed that actually these 3 DPP converters are physically very close to each other, and they can actually be integrated on one printed circuit board and controlled by one microcontroller. By one microcontroller. So that's exactly what we're doing here. Here is a high-level schematic of our hardware prototype. So we can see on one printed circuit board, we have one microcontroller controlling 3 DPP converters. And the challenge of this design is that how can you actually transfer, how can you send the control signal across different ground levels to the upper 2 DPP converters. And actually, we use a diode capacitor level shifting circuit, which proved to work well. And you're encouraged to read the paper for details. And to further shrink the size of our hardware, we actually use an integrated power stage, which is also known as DRMOS chip. So here the resulting hardware, and we put a counter for scale. So as you can see here, we integrate 3 DPP converters on one chip, on one PCB, and it can be well fitted in one junction box. So we can actually achieve PV junction box integration. And here is just a few specifications of the hardware. So I think it should be noted that it actually have a peak efficiency at 95%, and which I will show later. It can achieve a tracking efficiency above 99% of the system. So here is our experimental setup. So we test this algorithm with a setup of 6 submodules and 5 DPP converters. And these 2 DPP converters are actually implemented on 2 printed circuit board. And the communication between DPP converters are actually implemented through I2C interface. And we have a computer that collects data from all DPP converters. And it should be noted that this computer is not involved in the actual algorithm. It only receives information from the DPP converters. And the actual control algorithm is fully distributed in this DPP converters. And we also used electronic load here in constant current mode to emulate the central inverter. And here is a photograph of our experimental setup. So next, I'm going to show you some experimental results. Let's start with a system of 3 submodule and 2 DPP. So we have shown on the left is the simulation result of this system, and shown on the right. So we show all the state variables, D1, D1 hat, D2, and D2 hat. And here on the right, we show the corresponding experimental result. And as you can see, all these states actually, evolve following roughly the same trajectory. And to verify the correctness of this algorithm, we actually run the traditional centralized perturb and observe method here as a reference. So as you can see, they actually converge to the same final value, which prove that the effectiveness of our algorithm. So here is another experimental result of 6 submodule 5 DPP system. So again, we run the centralized perturb and observe method as a reference, and you can see after a kind of overshoot, they actually converge to the same final value. So let's just take another look back to our design objective to see if we actually achieve all of them. So we actually design this algorithm that achieves no current measurement and only neighbor-to-neighbor communication. But as the experimental results show, it truly realizes a true maximum power point tracking through a distributed approach. And in the hardware design aspect, we actually achieve a small hardware footprint that actually fit in a PV junction box. And we actually have still we are going to make a highly efficient converter with peak efficiency above 95%. So here are my concluding remarks, and this is the end of my presentation. If you have any question, please feel free to bring it up. Thank you.
Hi. Okay, so I have a question about when I think midway you have an example about taking, one loses communication.
Mm-hmm.
Can you go back to that slide? So is it that it replaces it, like does it skip a neighbor, or does it adjust even just without that data completely?
Yeah.
Without the communication?
Yeah, so how do you do this? Okay, I have a backup slide to answer that question.
Oh, great.
Yeah. So what is actually happening here? Like there's so here is what's happening. So in the update function, there's a matrix. There's a matrix called Laplacian matrix, which describes the graph of the system. So which is here. And once you have communication happen, like you can just locally, detect that communication failure, and you just need to change the corresponding part. Like for example, if you detect this communication link fail, then you just change these 2 points in your Laplacian matrix, and then you can just update the algorithm as before, and it will still converge to the same value. So you just need to change your update function accordingly. You don't need to make any change in hardware configuration. Just change within software. Yeah, so actually, like this matrix is actually distributed in all converters. So each converter only need part of it that concerns itself, so it can locally change it without, this one can just locally, converter 1 and converter 3 can locally change its own L without, making changes to any of other converters.
does it actually get?
Well, sorry.
Does it still get the communication? So if 2 goes away, does
Yeah,
3
if
get
this
the
one goes away,
one
then you have,
or
yeah,
is it just a lack
you only have this communication. You don't have direct communication between 1 and 3.
Okay, so we just go without that.
Yeah, I mean, Terry, do you have a better explanation for this?
Yeah, I mean, so you just need to have completely connected drift. And actually, connected drift, you only just have one device, every other device, as long as you have that. So in this example, you have like extra communication, like for instance, between 1 and 3, but also between 1 and 2.
Okay, so you have to have built-in extra communication links then?
Well, that's what I'm saying here. Yeah, the bare minimum is with neighbor to neighbor, that's like 1, 2, 3. So of course, you just communicate with them.
Okay.
So each one here you get extra neighbor to neighbor plus neighbor to neighbor.
Yeah, so basically, just as long as you can talk to, like, for example, if this neighbor-to-neighbor communication link fail, but if you can still talk to this one, and like talk to this one, this algorithm will still work. You just need to have a minimum communication for at least one communication link. Yeah.
How are you detecting the failure?
Well, I don't know. Just probably pin the other converter. I mean, this only works in simulation right now, but you can. Yeah, I mean, yeah. Yeah, I think so. Like probably you can just ping the other converter before they actually make the communication, and like if it, for example, ping is 3 times and no response, then they know they need to change L accordingly. Yeah.
Yeah. So I had a question similar to Catherine's. So when you change the communication network or the graph, like you remove that one connection, and then you can see like a huge perturbation in like the duty ratio, even though it's going to converge to the same state. I was just wondering why is that huge transient occur? Can you not like use your current times like your duty ratio, your current or your past time step?
That's an excellent question. I have a backup slide for that. So, yeah, that's an excellent question. So, like, so here is an example of, like, if you notice in the update function, besides L, we have another input, gamma. So this parameter actually affect, like, to what extent the input actually affect the change of state, like just how fast your input can change the state. So what is happening here is that once you change this configuration, then like before all the states settle to the new like final value, the input actually, there's a huge mismatch, so it can play a significant effect on the change of duty ratio. But what we can do is we can adaptively tune the parameter of gamma and potentially even this delta. So what we can do is, so in this example, like if we choose a large gamma, always use a large gamma, then we are going to have a huge overshoot as shown here. But if we always use small gamma, it's going to have a really slow convergence. But what we can do is we can like adaptively change it so it can, like in this example, like they both have their drawbacks, but we can combine them. We can, after a communication failure or something like a rapid change, and we can start with a small gamma to make sure there's no like large overshoot. And as these algorithm converge again, we can change to a larger gamma, which makes sure it can respond to changes in insulation like much faster. Yeah, I probably answered too much to that question, but yeah, sorry.
Like the gamma is using the update overshoot, but also the fact that you're estimating the derivative, right?
Mm-hmm.
And like you have different information now, so like what we saw before, you're not getting direct information to that communication link that failed, right? So now your estimate of the derivative is large, which is amplified by your gamma. So I think that's the reason that it happens by communication failure, right?
Yes. Yeah. Thank you.
So when you increase the amount of PV submodules, how does the number of iterations increase? to converge?
Oh, yeah, actually, yeah, that's a very good question. So I have a backup. Really, I have a backup slide for that. So yeah, so here is it's a simulation of a system of 6 submodules and 5 DPP converters. So like this is how it converges. But when we increase the number to 12 submodules and 11 DPP converters, then you can see actually converge like slower. But what we are, what we are trying to do is that, I mean, Terry, I should have your slide, is that as you go like further and further apart in the string, the actual, oh, no. Sorry. Okay, let me answer that question again. Indeed, like if you only have neighbor-to-neighbor communication, like you can see this significant difference. But as you increase the number of communication, like you can talk to your second neighbor, to your third neighbor, it actually, accelerated much more. And as you can see here, the difference between them are actually smaller and smaller. So by the design of integrating 3 DPP converters on one module, we actually have, by default, you can talk to at least 3 neighbors. So basically, 2? Yeah, basically we are, at, somewhere like this. As the number of converters and submodules increase, you definitely have slower convergence. But like through redundant communication, we can actually improve its property. So it's not very bad, I think.
Okay. Yeah. How does, like, I guess for the middle plot, that's sort of, I don't know for sure though. It would probably be like around like the optimal amount of redundancy, because otherwise you just have a bunch of like parallel communication links. So like how does that convergence speed match up with the dynamics of the central converter?
Sorry, you mean the centralized method, or?
Yeah.
No, how does compare to the centralized method?
How does that match up with like the perturbation speed of the central inverter and like the dynamics of the PV?
Sorry. Basically, your question is how fast can you accelerate this algorithm? Like, can you shrink the interval between updates? Is that your question?
Yeah.
Or,
well,
sorry,
okay, so this
really...
takes about like the middle one takes about like 4 seconds to converge, right? Is that too slow for like for the PV? Like for insulation changes in the PV?
Well.
Is that too slow for the outer slope?
Yeah. So here's what's happening. This is like a code startup, which means you start at the beginning of your day, like in the morning or something. So you have no information of the environment, like all the state variables are set by default to 0. So that's why it's taking like 4 seconds. It's like, once a day, you start in the morning and you take 4 seconds to converge. And once you actually fully converge, this is a really huge step change in insulation, which represent like the worst case scenario. You are not really likely to have a step change in real insulation. Yeah. But let's say even if you have, and it can actually, as you can see here, it will converge approximately to the final value within a second. That's like when you have a fully converged system, it can react much faster. So this beginning is only once a day when you start a system.
Right. Okay.
Yeah. Okay. Sorry.
We won't have a step change in terms of insulation change, but in the case of communication failure, you could represent that as step change like this.
Okay. So is when you have a communication failure, is that step change in the algorithm, like, is that too slow? Because like insulation, yeah, you'll never have a step change, but if you lose communication suddenly, that's more like a step change. So is that,
yeah,
like,
but
will this respond too slowly, or?
Well, but the thing is, insulation change happen very often during the day, but communication probably happen, months interval. Like, so it's, even if you are reacting a little bit slow on communication failure, it's still going to be okay because it happens so rarely. You are not really losing much power because of that. So yeah, that's what I think. But again, like as you can see here, even if you have a really just communication failure, it can still converge within a second or two, and it's still back to normal. So I think the real challenge is how you detect the communication failure. That's probably going to take some time.
To address the last two questions, it's not the end of the world if sometimes you don't rack fast enough. It means that for that little cycle, you're losing a fractional percent in power. It doesn't. You don't have to. You have to. If there's a kind of rare event, you don't want to design your system to respond, to that, one, fractional percent probability. So it's not the end of the world if you don't track it every time. Nothing's going to get fooled. What? Always going to get fooled. That's right. Yeah. As long as it doesn't explode. No, but nothing bad will happen by you missing a cycle. No, to make a habit out of it.
Okay, thank you.
So Shibin, does a flock of geese count as a step change?
Sorry, what's that?
Does a flock of geese count as a step change?
Sorry.
Could we just take just a couple minutes and talk about EOH real quick? We're running out of time. I was just wondering if we could get 5 people to head up 5 projects that need some updates.